Thank you, Michael. Yes, so today I'm going to talk about multi-object tracking. It's a bit of a, so I will present a little bit of the past work that we did, and then talk about open problems or things that I think are where the community is not quite there yet. And I would especially, of course, there's a focus on the discussion, right? So I would present especially controversial results, and let's see where the discussion leads. So let me start by briefly presenting the task. So in multiple object tracking, our goal is to detect and track all objects in a scene. And usually these are the type of scenes that we're looking at. The objects are usually all of the same type, so either pedestrian tracking or car tracking, and we have a lot of them. So there's a lot of occlusions, there's problems with different viewpoints, and therefore there's different levels of occlusions depending also on the viewpoint of the camera. And we can also have moving cameras. So these are all types of scenes that we want to deal with a single algorithm. So usually back in the days, people started approaching the problem of multiple object tracking by dividing it into two steps. So the problem is a little bit too complex. So people say, okay, let's break it into two steps. And they call this a tracking by detection paradigm. So the first step was to take individual frames and perform detection on each frames. So you would have a set of proposed locations where your object of interest are lying. So these locations, of course, they don't need to be perfect, right? So detection is a field and a task on its own. So you can have some false positives here. Like, for example, the blue boxes are the errors that you have in this sequence. Sorry, the yellow boxes. And then you would have a second task, which is data association, which would try to recover the trajectories, the complete trajectories in this video. So link these detections in time. And of course, any error that you have in the detection step is makes the data association a harder task. Now, this is the paradigm that was valid, I would say, up to 2-3 years ago. Then other paradigms started appearing. So this is sort of an evolution that we did with our dataset mod challenge about the methods that submitted to this benchmark from 2015, 2016, all the way to nowadays. And you can see here a nice trend, right? So people were in the 2015, 2016 period, they were working a lot with motion models. So you can see all these methods in orange. They were also working in data association, so a lot of graphical models were used at the time, batch-wise processing of sequences. And you can see how data association brought quite a lot of an accuracy increase. So you see in the y-axis the accuracy of tracking, how we measure it with this MOTA score. And only recently, a new paradigm started appearing, which we call tracking by regression. And now I will present one of the first works in that tracking by regression paradigm, and how this brought a bunch of other open questions. And this is, I think, where the discussion will be a nice follow-up. So if we look at this paradigm again, we have the detection, we have the data association. People were working a lot with data association, and they considered detection as, well, you know, any thing that we can do in detection, perfect. We just take it in tracking, but mostly we work in the data association domain. So what we did in 2019 was, well, let's take a step back. And instead of looking only at the data association, let's start looking at the detector from a tracking perspective. So what we did there is we focus on the then popular regression-based detectors, for example, faster CNN. And how they work is you have an input image, you have a series of convolutions to obtain a feature representation of that image. And then you have a bunch of region proposals that tell you, look, this is an interesting, particularly interesting part of the image. Let's look at the feature representation of that part of the image, and let's try to make sense of it. So let's try to classify it. Is this a person? Is this a car? Usually this classification has a semantic tag attached to it. And then the interesting head for us is the regression head. So what does this regression head do? We have these region proposals, which are not perfectly located around the object sometimes. So you could have this sort of shifted bounding box. And then what the regression head does is it takes this bounding box and it regresses its coordinates until it fits tightly around the object. Now, this is, of course, particularly useful for detection because the more you overlap with the ground truth bounding box, the better accuracy you have. So this regression head is very useful to increase accuracy in detection, but it's also very interesting for tracking, right? Because this notion of moving bounding boxes is something that can be used for tracking. And so this is essentially what we proposed in 2019. We said, well, let's use these regression capabilities of detectors and use them for tracking. Because this is very similar in the end to what we want to do in online tracking. And by online tracking, I mean tracking from one frame to the next. So not using batch-wise tracking. And so what we proposed at the time was what we call a tractor, which was a method trained for detection, but with tracking capabilities. So how do we do that? Let's assume that we are at frame t+1. So we have already tracked these three persons, in this case, up until frame t. And now what we do for frame t+1 is we use the detections of frame t as proposals for our detection network. So these are, of course, detections that come from trajectories. That's why I assigned them different colors, because we do have tracks for these people. But you also see that the bounding boxes are not perfectly located because people have moved from one frame to the next, which means that these bounding boxes are not going to perfectly fit the position of the pedestrian in frame t+1. But that's exactly what regression is for. Right? It can really regress the bounding box locations of these three pedestrians to tightly fit the position, the new position in frame t+1. So now the question is, in order for this to be a tracker, I need to be able to answer the question, where did the detection with ID1, let's say the red detection, where did it go in the next frame? Can I make a link between the detection in frame t, which is the location that you see on the left image? Can I make a link with the position at frame t+1? Since I know that this bounding box, the red bounding box, was obtained by regressing the red bounding box position on the left image, I have now linked these two positions. So effectively, what I did with this regression head is to perform tracking. Now, the cool thing about this is that we don't even need to train this, right? We can just reuse extremely well-trained regressors. They are trained on really large-scale data sets. They are really good at regressing, so we get really well-positioned bounding boxes. If you have then another data set, let's say we want to repurpose this for cell tracking, you don't need to annotate videos, which is much more tedious than actually annotating images. So you can just annotate images, train your detector with it in a faster CNN manner, and then you can use it and repurpose it for tracking. And of course, another pro is that Tractor is actually online. So you can do real-time predictions if your network is, if the forward pass is fast enough. Now, of course, this is an extremely simple tracking method. So there's also some disadvantages with it, right? So the method has no notion of identity. So it just regresses the previous box to the closest pedestrian in the image. So there is no notion of identity. So in crowded spaces, it can get easily confused. Then you have the con of any online tracker that the track is killed if the target becomes occluded. That's a problem for any online tracker. So you need another method to close small gaps and occlusions. Now, this can be easily solved with methods that have already been used in multiple object tracking before. So we don't need to reinvent the wheel here. We can just repurpose some of the methods that were already used before in multiple object tracking. And for the third con, which is actually that the regressor only shifts the box by a small quantity. So FastRCNN is specifically trained to regress only small quantities. And we try to train it for regressing bigger quantities, and this drifts very easily. So the disadvantage with that is that if you have large camera motions, if you have large displacements due to low frame rate, then the regression doesn't quite catch up with the pedestrian. Again, for this, we have many methods that have been used before in multiple object tracking, like motion models, for example, and we can repurpose those to try to overcome these disadvantages. So with these very two simple ReID and motion models, we can actually reduce the number of identity switches, which is the measure that we typically use to see whether we're actually performing tracking correctly. So beyond detection, are we actually keeping identities correctly or not? We can see that with these two very simple add-ons, we can actually preserve identities in a much better way. So you have right now a very simple method, which seems to have a lot of disadvantages, but this can be easily corrected by methods that were already used in tracking, by re-identification methods, by using motion models as simple as constant velocity motion models. So at the time, these were state-of-the-art results. I have to say we were a bit surprised. So what we did then was we said, well, let's look at what the other trackers are doing, right? It is very weird that with such a simple method that we barely trained this tracker, right? This is essentially a repurposed detector. How come we are so good at the tracking problem? And especially, what are all the other methods doing? So here, what I'm showing here, you have the bounding box visibility in the x-axis. You have the percentage of tracked bounding boxes, which you will see here in these thin bars for different methods. And the thick bars are the occurrences in the ground truth. And with this, what I want to show is that there's a lot of boxes that are completely occluded. So these are these boxes that have 0% visibility, but most of the boxes are completely visible. So 90% to 100% visibility, which means that pedestrians are clearly seen, you can re-identify them, etc., etc. So a lot of the data in Mod Challenge is actually very easy. So this means that whenever you compare a method with accuracy, you start comparing methods. A lot of them do really, really well on these easy scenes. And so essentially everyone is fighting for this middle ground here where there's intermediate visibility, because for zero visibility, all trackers suffer. So here what I'm plotting is different methods that were popular at the time with different paradigms. We plotted their accuracy here, and we also plotted the tractor accuracy with or without the ReID and the motion model. So the plus is the one that has the ReID and the motion model. Now, the interesting thing is this area here, right? So the area where trackers start to suffer, so the accuracy starts to go down. But we see that our method, tractor, which is these two lines here, it's keeping up quite a much higher accuracy than compared to other methods. And especially methods which use graphical models, like for example, the JCC method. You have this method here in sort of light blue. This method creates a graphical model of the sequence and tries to solve occlusions, right? That's what people in the community think that graphical models are for. You create a huge graphical model of the sequence, and this will allow you to overcome occlusions because you will be able to link bounding boxes which are far apart in time. Well, it turns out this is not really the case, right? So you have to be conservative also with graphical models, otherwise you just create a bunch of false positives. So in this being conservative, what eventually this happens is that once you hit bounding box visibility 60%, your accuracy really goes down. And maybe contrary to what you would intuitively think, an online method like Tractor is actually keeping up quite a good accuracy. So what we learned from this paper, we have also other analyses in the paper, and I invite you to look at them there. But what essentially we learned is that the hard problems in tracking are left unsolved. So the coverage of large gaps in detection or the long occlusions, but even the partial occlusions. So as soon as you hit this 60% visibility of the pedestrian, which usually means that it's occluded by another pedestrian or by a tree, for example, in the scene, this is already a hard case for tracking. And of course, the tracking of small targets, because if you're relying on detections and detections don't work for small targets, you don't even get a trajectory to start with. And so what we found is that all the methods were just sort of fighting for these easy scenes. These scenes with visibility above 80%, they were fighting there. And this means that the accuracy in tracking only increased very, very marginally in the last 2 years of mod 16. So this is the main challenge in mod challenge in our benchmark for multiple object tracking. And we saw that in 2 years, people just increased the accuracy by 2.4 percentage points. So then we said, well, what we need to do is we need to move forward, right? We need to get rid of all these easy scenes. We can just use Tractor for the easy scenes, which is essentially repurposing detection. We can use basic ReID, basic motion models to sort of cover all these easy scenes. And then the community, the tracking people should focus on the harder cases, should focus on these long occlusions and should focus on these extremely crowded scenes. This is where the hard cases are, and Tractor cannot really solve this. So then we said, okay, let's focus on those scenes, right? Let's try to really recover long occlusions and extremely crowded scenes. So then we went back to the community literature, especially before deep learning, and we said, okay, what were people doing there? Can we really repurpose that for the modern problems that we have in tracking, these long occlusions and extremely crowded scenes? And if you look at the literature, typically long occlusions are recovered by using re-identification methods. So you have a really high frame rate nowadays in multiple object tracking, which means that you cannot really create a graph with many, many thousands of frames to recover really long occlusions. So what people typically do is they resort to re-identification, which means that your person, you're tracking a person, a bounding box disappears because it's occluded. You store the appearance of the last bounding box or the last n bounding boxes, and then you start comparing with the bounding boxes that are reappearing, are being redetected, but you don't know which identity they belong to. So you try to re-identify this person that has been occluded. And so at some point you hope that it will reappear in a future frame and you will re-identify it and then link it with the detection where the person disappeared. For extremely crowded scenes, people, again, were using graphical models to disambiguate these occlusions. So this is also where we wanted to go. So we worked on graphical models. First, we said, well, you know, in the area of deep learning, we have graph neural networks. We can use this to actually learn this data association, right? We don't need to handcraft it anymore. So what we did just briefly here is to construct a graph with appearance information in the nodes. So typically a graphical model for multiple object tracking means creating a graph where each node represents a detection. And then optimizing this graph so that you obtain the valid links between detection. And an active edge or an active link means that these two detections belong to the same person and therefore create a trajectory. So we can do exactly the same here with modern tools, with CNNs, with graph neural networks. And now the cool thing about this is that you can optimize both the appearance, which is encoded by a CNN, as well as the data association, so finding which links are active or not. You can optimize this all together with neural message passing or with graph neural networks. And essentially what you're optimizing for is the end goal, right? This edge classification that tells you which two bounding boxes belong together or not. So this is sort of looking back at what we used to do in data association with graphical models, but saying, hey, now you don't need to handcraft features, you don't need to use classic optimization methods, but you can put all of this together and repurpose it for multiple object tracking, what we call 2.0. So, okay, this worked really nicely, but again, we cannot really do solve long-term occlusions with this. We cannot create such a large graph. And so we still need strong re-identification scores. And now the question, and here's what I find it a bit controversial, is that we went back to the re-identification sub-community, which is sort of, you know, they're doing their own thing. They're developing methods for re-identification. And we said, okay, do they really work for tracking? So the first thing that I'm going to plot here is sort of an accuracy versus relative size between the two bounding boxes that are being matched. And what we found here is that if the two bounding boxes are of very similar size, then ReID works pretty well. If the bounding boxes start to vary in size, which could happen, right? After an occlusion, the person could be coming closer, but behind a tree. Suddenly, the bounding box that reappears is smaller, and your accuracy has gone down quite a lot. So ReID doesn't really handle varying sizes well enough. Another thing that we plotted is that maybe like contrary to common knowledge, ReID has difficulties recovering long-term occlusions. So we plot here the accuracy with respect to the frame distance, and we see that as soon as we go 20 frames away, which could mean less than 1 second if you have a high frame rate, the accuracy completely drops. Which means that this is not really useful for long-term occlusions, right? Long-term occlusions could be many seconds apart, could be thousands of frames apart, and this is not really working with classic ReID methods. And the third thing that we started plotting is, you know, how does ReID work when we have partially occluded objects? And the bottom line here is that we plotted a bunch of accuracies. The different colors mean different levels of visibility. And what we can see is that ReID can only re-identify partially occluded objects if they are similarly occluded. So if you have an object occluded 40%, and it suddenly reappears somewhere else and it's also occluded 40%, then it can be re-identified much better than if it reappears and it's only 20% occluded. So there seem to be very specific cases in which ReID works, but these are not really the cases that you will find in tracking. So what I find here is that long-term ReID, or let's say recovering for long-term occlusions, means that the boxes are far apart in time, they are potentially of different size, and they have different rates of occlusions. And these are exactly the three things where ReID is not good at. So now where I would like to start discussion is, well, we had all these hard problems in tracking which were left unsolved. We think that we can solve them with ReID, but now we find that classic ReID methods, how they are trained, maybe the data that they use doesn't really allow them to solve these problems in tracking. So ReID seems to really struggle with those scenarios. So the question is this the right technique? Are we training it wrong? So this is where I want to start a discussion. Before, of course, I would like to thank the people that actually worked in these projects that I've presented. And now I would open the floor for discussion.